Hello and welcome to Classes with Atish. As you can see, I am not in my basement today. I am not using the light board, but today I am going to use my whiteboard. I am in my study. This is my library come study, and I spend most of my time here. So I figured I should have some arrangement to record videos in my study room so I can produce more videos. So here you go. So today we will talk about pseudo forces. I had introduced the concept of pseudo force and non-inertial frames of reference in a past video. If you want to go ahead and check that out, I will put a link to the video right here on the screen. But we'll focus more on pseudo forces today. Okay, so let's get started. Okay, pseudo force means it's not a real force, it's an imaginary force. So where do we really need pseudo forces? So if you remember Newton's laws of motion, apply to inertial frames. In fact, Newton's laws define an inertial frame. What is an inertial frame? An inertial frame is one where the frame itself is at rest or is moving with a uniform velocities, that is, it has no acceleration. An example that we went through was the case where, let's say you are in an elevator, okay, and let's say there is a string and there is a mass attached to that string. Okay, there is an observer inside the elevator. We'll call that observer A, and then there is an observer who is outside the elevator on the ground. We'll call that observer B. Okay, now let's suppose this elevator is going up with an acceleration A. Okay, now this observer A, who is inside the elevator, he is a learned man. He looks at what's going on with the mass, and he writes down his Newton's laws of motion. Okay, so he writes down, person A writes down this. He sees the mass is attracted by gravity, mg, and then there is tension in the rope. Okay, and he calculates tension as T equals mg, because for him this body is at rest, it is not moving anywhere. Let's see from a perspective of person B. Person B, he can see the entire system. The elevator is going up with acceleration A. So what he will write is, there is tension in the string, there is force due to gravity on the mass, and this entire system is going up with acceleration A. So he will write T minus mg equals ma. So which gives T equals mg plus ma. Now who is right? Is tension equals mg, or it is a little bit more than mg, depending on the acceleration of the elevator? Now what did A do wrong? Obviously B is right, because inside the elevator, if the elevator is going up, you feel like your weight has increased. This tension is nothing but the weight, right? If you replace this string with the spring, or let's say a weighing spring, then it will register your weight, right? You will see your weight appears to be heavier if the elevator is going up, and it appears to be lighter when the elevator is going down. So obviously this is a correct representation of the tension, and this is not. But why did we fail to apply Newton's laws of motion correctly in the case of observer A? The reason is, observer A is not an inertial frame, it is a non-inertial frame. And you cannot apply Newton's laws of motion correctly in non-inertial frames. So what do we do now? How can we correct this? The way to do that is, if we are dealing with non-inertial frames, then you introduce what is called a pseudo force. And the pseudo force we will introduce here in the opposite direction to the acceleration of the frame. So it will be in the downward direction. So let's say this is the pseudo force, Fs. Okay, and what we will do is, pseudo force will be equals to the mass of the body times the acceleration in the opposite direction. Okay, now can you really figure out that force inside? No, that is the reason it's called pseudo force. It is an imaginary force, it's not real. But to be able to apply Newton's laws of motion to a non-inertial frame, we introduce the pseudo force. Now with the pseudo force, if we write the equation, A will look at it as T, so sum of all forces, right? T minus mg minus Fs is equal to 0, because for him there is no acceleration of the body m. Okay, so now if I write down T minus mg minus ma equals 0, T will come out to be mg plus ma, which is the same result that we got when we applied Newton's laws in a inertial frame of reference. Okay, so that is how we introduce pseudo forces. Now let us solve some problems using pseudo force so it becomes even more clear. Okay, let's say there is a car. Okay, and the car is moving this way, and there is a mass attached to a string from the top of the car. Let's say the mass is m. Okay, and the car is moving ahead with an acceleration a. So what will happen if it moves ahead with an acceleration a? At some point the mass will make an angle theta with the vertical, and it will stay at rest, right? Our goal is to find this angle theta, find theta where the mass is in equilibrium. Okay, now if you are an observer inside the car and the car is accelerated with acceleration a, then that for that observer it is a non-inertial frame, because that frame is the reference frame is moving ahead with an acceleration. It is not with an uniform velocity, it is not at rest. Okay, so if I draw the free body diagram of this mass m, we'll have a force due to gravity mg. There will be tension in the string, okay, which makes an angle theta with the vertical. Okay, and we also have to introduce a pseudo force in the opposite direction to the direction of acceleration of the inertial frame, and that pseudo force magnitude will be the mass times acceleration. Okay, now for the observer inside the car, this system is at rest. Okay, so what we can do is we can write down two equations. T cos theta minus mg should be 0, and T sin theta minus ma should be 0. Okay, so from here we can find T cos theta is equals to mg, and T sin theta is equal to ma. If I divide this by this, then T cancels out, so tan theta equals a by g, or theta is tan inverse A by G. Okay, so this we solved using the concept of pseudo force in a non-inertial frame. Now let's say there is another guy who is on the road observing everything. Okay, for him it's an inertial frame of reference. For the car, for the guy inside the car, it was a non-inertial frame. Right? Let's try to solve this using this observer, the observer who is on the ground, which is an inertial frame of reference. Okay? Let's look at that. So, now for him, the free body diagram will be this. mg, there is tension in the string, okay, and this makes an angle theta, but he can see that the entire thing is accelerating with acceleration a, so there is a net acceleration in this direction. So t cos theta, which is the component of tension in the vertical direction, minus mg is 0 because it is stationary. There is no motion in the upward or downward direction. There is only motion in the towards the right. And the component of tension in the horizontal direction, t sine theta, is responsible for the acceleration, so mass times a. So now from this we get t cos theta equals mg, and we arrive at the same two situations. We get tan theta equals a by g. Okay, so theta is tan inverse a by g. So you can solve any problem in a non-inertial frame as well as in an inertial frame. But often it is found out that if you solve the problem in the non-inertial frame introducing a pseudo force, it becomes easier to solve it. So that is the beauty of pseudo forces. Okay. Now let's look at another problem where we will deal with a non-inertial frame and see how we can apply the pseudo forces to solve it easily. Okay. So let's suppose there is a spring balance, okay, it's connected to a massless pulley, and on one side of the massless pulley we have a 1.5 kg hanging, and on the other side we have a 3 kg mass hanging. Okay. Now let us put all of this inside an elevator, and the elevator is going up with an acceleration of g by 10. Okay, the problem is find the reading on the spring balance. So whenever the question is asking for find the reading on the spring balance, all it means is we have to find the tension in this. Okay. Okay, how do we solve this? Now if we draw the free body diagram of the 1.5 kg, this is what we will do. So there is 1.5 g, so this is the force due to gravity. There is tension in this string T, okay, but the entire frame of reference is accelerating with acceleration g by 10. So we have to introduce a pseudo force in the opposite direction, which is downward direction, and the value of that pseudo force will be 1.5, which is the mass, times g by 10. Okay. Now similarly, let's draw the free body diagram for this 3 kg. Oh, one more thing. Internally, this 3 kg will come down with an acceleration a with reference to the frame of reference of the elevator. And if this is coming with an acceleration, coming down with an acceleration a, because this is a continuous string, this will go up with an acceleration a. But this acceleration a is as measured by the person inside the elevator, which is a non-inertial frame of reference. Okay. If a person was outside the elevator on the ground, he would not measure this as a. It will be something different, and it will become more complicated. That's why we move inside the elevator and solve this in a non-inertial frame. Okay. Now, so if 1.5 kg is going up with an acceleration a, so this system is going up with an acceleration a. Now similarly, let's draw the free body diagram of the 3 kg. So 3g, we have tension. We have to introduce a pseudo force in the downward direction, but for this one the pseudo force would be 3 times g by 10. Okay, and then this guy is going down with an acceleration a. Okay, now let's also look at the free body diagram of the massless pulley. So there is, let's say this tension is T dashed. So there is tension T dashed, and then it is supported by 2 tensions in the downward direction, so 2T. Should we introduce a pseudo force here? Absolutely yes, because this is also in the non-inertial frame. But what will be the magnitude of the pseudo force? Because this is given, it's a massless pulley, so it has no mass, times g by 10 in the downward direction. So because it's a massless pulley, we can just eliminate the pseudo force there. We don't need to write it. Now that we have the free body diagram of all the 3, let's write down the Newton's laws of motion, apply that and write down the equations. So it is going up with acceleration a, so tension must be greater than the sum of these two. So T minus 1.5 g minus 1.5 g by 10 is equal to 1.5 a. Mass times acceleration, right? So what are we doing? Sum of all forces is equal to the mass times acceleration. That's Newton's second law. Okay. For this one, so acceleration is downward. So 3g plus 3g by 10 minus t will be responsible for the acceleration 3a. And for this one, okay, one more thing I wanna. So these are all happening as observed by the observer inside the elevator. Now, what does the observer see about the massless pulley? Is it accelerating anywhere? It is going up, down? No. For him, it is at rest. These guys are, this is coming down with some acceleration, this is going up with the same acceleration, but the pulley is at rest. So for him, T dashed minus 2t should be equal to 0. Okay. Now let's solve this. So T minus, we'll put down value of g, 10. So 1.5 times 10 minus 1.5 times 10 by 10 equals 1.5a. T minus 15 minus 1.5 equals 1.5a. So T equals 16.5 plus 1.5a. From here, 3 times 10 plus 3 times 10 by 10 minus t equals 3a. So 30 plus 3 minus t equals 3a. So 33 minus t equals 3a. Now if I multiply this equation by 2, so 2t equals 33 plus 3a. Now we have 3a is 33 minus t from this equation. So this is 66 minus t, or 3t equals 66, or t equals 22 Newton. Now if t equals 22 Newton, what is our question? Find the reading on the spring balance. So we have to find t dashed. So t dashed is 2t, or 2 times 22, which is 44 Newton. So that is our answer.